Okay, everybody clear on that? If you submitted the mini exam 7 via email, please bring that next class, all right? If you submitted the mini exam 7 via email, bring it next class unless you have it today. Got it? All right. Might be loud. Ooh. Okay, I had everything opened up, but not anymore.
Did you all finish green here last time?
We did not. Oh yeah, and by the way, the video, I did not upload that storm on Thursday. We had a lot of damage at our house, so I've been busy fixing fences and other things, cutting up trees. So I forgot my camera here. Thursday after class, they canceled all classes, and I left, and I forgot the camera here. So I will get it uploaded.
Yes, sir.
What is going on with this damn thing?
Oh yeah, no, it like a good thing you don't read breakers like my late fan was
Does everyone have that handout that I gave y'all last time?
Still need one on Thursday.
Still need one?
I don't think I got a handout.
You were gone. Yeah, you were out.
I only have a few, so I will. There we go.
Well, if someone wants this one, I can always write on your paper. I'll just take a picture.
Here we go.
If there's not enough, you guys can have mine, and I'll just.
I have 4 copies. I'll put one here. Y'all can share that one.
Sounds good to me.
There. And then we need one back here. Okay. You have yours. Thought maybe I had some extras over here.
Is it okay if Nick has this one?
What's that?
Is it okay if Nick has that one?
What was your question?
Who's asking like this?
Yeah, there's no assignment there. We're gonna use that today. Yeah, we're gonna go over that today. Okay, so let's get started. We're ready running behind now. Thanks to technology. All right, so last time we were covering 3.5, we talked about the curl of a vector field and how we can use the curl of a vector field to determine whether or not a vector field is conservative, right? If the curl gives you the 0 vector, you have a conservative vector field. So now we move on to the second operation on vector fields. Where is all this? Right here. It's called the divergence of a vector field. So the divergence of a vector field, if you're given a vector field, PQR, 3-dimensional vector field, and the partial derivatives exist, then the divergence of that vector field, which we denote div f, is just the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. So all you're doing is taking the derivatives of p, q, and r respectively with respect to x, y, and z, and just adding those up. And so you get a scalar out. Remember when we did the curl, you did a curl and you get a vector out, right? That gave you something, it has to do with the axis of rotation of something. So your answer here will be a scalar. The notation we use for div f is del dot f, as opposed to the notation for curl, right? The curl of f was del crossed with the field, right? We're now saying that div f is del dotted with the field. And I talked to you last time about how we can look at this del as this thing we call a differential operator. So it's just the del gives you instructions on what to do. So here we go. Here's a vector field. Right, here's a vector field, and we want to find the divergence at the point 2, 1, 0. And we'll talk about what the divergence means geometrically here in a minute. Let's first just make sure we can do the computation of it. I think you'll find that the divergence is much easier to calculate than curl. So let's first write div f, right, is del dotted with the field, which del is the vector partial with respect to x, partial with respect to y, partial with respect to z. We're going to dot that with the field P, Q, R. I'm just writing out the definition, which is above this note, all right, just so we can see it again, which is the partial of P with respect to x, partial Q with respect to y, partial R with respect to z. And now for this particular example, let's do these partials. So, oops, sorry. We're doing this is a dot. My gosh, Robert. Plus equals. All right. Right, when you dot them, you add each one up. All right, partial of P with respect to x. So here's P, what's the derivative of that with respect to x? 2xyz, right? 2xyz plus partial of the Q, right, with respect to y would be same thing, 2xyz. And finally, the last one is 2xyz again. And add all those up and you get 6xyz. There you go. That's the div. That's the divergence of that field. Yes?
Would we plug in our values that it?
Yeah, so that's the divergence of the field, right?
Okay, that's diversion of the field.
Now we want a divergence at this particular point. So at the point 2, 1, 0, we get the divergence is equal to 6 times the x times the y times the z, so 0. Let me mute my phone. I'm part of the HOA association. There's a bunch of shit going on. We got trees down everywhere, so mute that, sorry. Okay, yes? 0? Pretty boring example, divergence 0. But do you see how the calculation is much easier? You don't have to do a cross product, so it's much nicer, no formulas really to remember. I mean, if you remember this and you remember what a dot product is, you're in business. Okay, now, what does the divergence represent? So let me do a recap of curl. You were all very impressed with my dancing the other day, right? So I think that the best analogy of curl was like a baseball, right? So you imagine a particle that's moving. It might have a direction, which would be like the direction of the field. You know, so the field gives you vectors. So the direction of the object would be your field, but it could be spinning at the same time. And it doesn't have to be spinning on the same axis as the direction it's moving. So even though the ball may be going this way, it might be spinning on an axis, a different axis, right, as it moves in that direction. So that axis of rotation is another vector, and that is the curl vector. And the magnitude of that vector is how fast it's actually spinning, right? So that's what we did last class. Now we talk about divergence. So what does that represent geometrically? Well, here's kind of the definition of it. If the vector field represents the velocity field of a flowing fluid, so going back to the idea of like particles moving through space, water, something like that, then the divergence measures the tendency of the fluid to diverge or leave a point of the fluid. Okay, so what does that mean? So you got this ball moving through space, right? It's got its curl, it's moving, but there's also other balls moving around as well. So you have these molecules of water or something, right? And each one of those has its own direction and it has its own curl, right? Everything's, unless it's a conservative vector field, then there's no curl, right? For all of them, they're not spinning. So if you were to take this ball in the center and just start to look at the balls around it, are they moving away or are they coming towards that ball? What's their tendency? In that little neighborhood around that molecule, are most of the molecules wanting to move away or come towards, right? So here's the geometric illustration. Here's that molecule, right? Right now, we're looking at that molecule as like this infinitesimally small point, all right? So we have this point, and if you look at that point and make this little tiny shell around it, right? So imagine you have a point, and we create a little shell around that, and then we start looking at all the points on that little shell. The question is, are those points going away or coming towards that center point? And so right now the divergence, I'm having it calculate, the computer's calculating divergence for this particular vector field. I'm getting a positive answer. Y'all see that? Okay, so let me show you the actual divergence. So this is taking all these points, like I took a point and I found that vector right there is not the curl, that's the vector field vector. And I'm doing all the little points around here, all the vector field vectors for all these points. Anything that's in green is moving away from the surface of that little infinitesimal ball. Anything that's red is going into the ball. That makes sense to you?
So a positive value indicates mostly away.
That's right. So the net total is that you have more going out than coming in. Some vectors are pointing into it, some vectors are coming out, but the net, right, the positive take away the minus, you're going to have plus. And that's why we're getting positive divergence. Now, if I move this point around, my divergence is going to change because we are in a vector field. So the vector field has an impact on the divergence, right? So here we can see we have more going in than we have coming out. Let me see here, hold on. Let me zoom this. Let me zoom in on the ball. Okay. Can you all see that these vectors are going into the ball and then the green ones are coming out? Yeah? All right, let me move it around to a different. Notice I have negative divergence. Yeah, there's more coming out than going in, for sure. Wait, did I say that right? There's more going in than coming out, sorry. Let me see, move it here. There we have more going out than going in, right? I can have more vectors, but I'm definitely going to slow my computer down. There's more vectors. Let me zoom out. Okay? That's what divergence is, all right? Now, that's in the three-dimensional vector field. Let's look at a two-dimensional vector field. Do you remember what curl looked like in 2 dimensions? It was like a paddle wheel, and it created the spin. Okay, divergence here, let me back this up so my computer's not freaking out. In 2-dimensional, what we do is we imagine, again, a point, right? And this point is, the curl is going to determine whether or not that point's actually turning as it moves through, right, as it flows. It might have some curl to it. The divergence is taking a small little circle around it and looking at all the points around it and seeing if those points are moving away or coming towards. So here it is. Right now my div is 0. That means the total out should equal the total in. Yeah, can y'all see it? You have vectors going out and you have vectors coming in to the circle, and they cancel each other out. If I move this to a different place in the vector field, still div of 0, right? Still div of 0, because the back side, those are going into the circle, and then on the bottom side, those are coming out, and they're just offsetting each other. So div is 0. This is a pretty boring vector field, it looks like, right? Looks like we're getting div 0 all the time, no matter where I am. So let's change the vector field. Let's do a different vector field, like this one. And now we no longer have div of 0. Depending on where I am, I can impact the div. Make sense? Going away, coming in. Divergence. All right. There's a note here that I somehow skipped over here. Okay. So given some point in 3-dimensional space, right? If the div is positive, then the region around the point is called a source. I think of it as like electricity, right? Or like heat almost. You have this point, right? And the div, if the div is positive, you have more coming out, so it's a source, right? If your div is negative, then the region around the point is called a sink. It's like almost like pulling everything in. Not everything, but just pulling more in than it is pushing away. And finally, if your div is 0, then the region around the point is called incompressible. Incompressible. There was a definition last class for something called irrotational, and that's when your curl is the 0 vector. If your curl is the 0 vector at a point, that means you're irrotational at that point. If your div is 0 at a point, then we say that it's incompressible. All right, the last two notes here are just, well, this first one is the one that's more important. The second one is just because it's in the book, I wanted to put it in here. I wanted y'all to see an alternate notation for the work vector that we, or the work integral that we had been working with. Remember this integral right here can be written as the line integral, right, over the closed curve C of P dx plus Q dy plus R dz. That's another way to write this. According to this, that's equivalent to this right here, right? So what is this piece right here? That is, well, curl of f. I'm just going to write curl f. Curl f. And then I'm dotting that. What's k? What is, this is the, think ijk. K hat, that's actually supposed to be k hat. So what's the k hat vector? 0, 0, 1, right? 0, 0, 1? That's k, right? What happens if you dot these two vectors together? You only get the z component of the curl, don't you? You only get the z component of the curl. Let me go back up to your notes. What's the z component of curl from last class? There it is. Here is curl, the definition of curl right here. Look at the z component, right?
That was the test, right?
Pardon?
That was the test for conservative.
That was test for conservative for two-dimensional vector fields, right? But what we're saying here is that this line integral is equal to the double integral, right, of this vector dotted with this vector, which just leaves you with this, right? So here it was, right there. Okay, so this work integral is this, but that should be equal to the double integral of the dot of these two, which was partial q with respect to x minus partial p with respect to y, dA. This is over the region D. And this is Green's theorem. This is Green's theorem, right? Green's theorem said that if you want to do this work integral, that all you have to do is this. Right? It's just another version. It's just showing you that this notation can be used to be equivalent to Green's theorem. Not majorly important. We're done. We're moving to 13.6. This is not, that's the handout. I don't want that. I want this. All right, recall back from chapter 10, chapter 9, chapter 10, sorry, chapter 10. We talked about vector functions. Vector functions are functions that draw curves in two or three-dimensional space. I wanted to give you two reminders. Here's one. Here's the way we wrote it. I'll put it on the side here just so we have it. It was r, the vector r of t equals, in this case, t squared 1 minus t cubed, right? If I graph that, it draws me a bunch of vectors that trace out a curve, right? A curve in two-dimensional space. If I do a different vector function, like this one, cosine t sine t, t over 5. That will draw me a curve, right? A curve in three-dimensional space, right? There's the, it looks like the spring. We did all that. Now what we're going to do is talk about parametric surfaces, not parametric curves, but surfaces in three-dimensional space. And what we want to do is we want to be able to draw a surface, not using the standard equation of a surface, but using a vector formula or vector function. So we've already studied surfaces, right? Like if I wrote down x squared plus 2y plus z equals 3, we all know that that's a plane, right? If I do something like x squared plus y squared plus z squared equals 9, we all know that that's a sphere, right? Radius 3. We know how to draw surfaces already, don't we? But they were equations that involved x, y, and z, not vector functions that drew those surfaces. We want to draw a surface with vectors instead. I don't know, do y'all remember, it was a long time ago, I said, hey, we can find the vector equation of a line, right? The vector equation of a line. And then I said, do you think that there's a way we can find the vector equation of a plane? He said, yes, there is, but it won't come till chapter 13. For now, the equation of a plane is this, all right? So now we're ready for parametric surfaces. There's the definition right here. What we're going to have now is a vector function. Okay, it's still going to be r, but instead of taking in one variable t, it's going to take in two variables. In the standard notation is to use u and v. So it's going to take in two variables, and what is it spitting out? A three-dimensional vector. The first component is a function of those two variables, u and v. The second component is some other function, and the third component is some last function of those two variables. As u and v take on different values of the function, the function generates a surface in three-dimensional space. These functions are called the parametric equations of the surface. So these are the parametric equations of the surface right here. So let's look at an example. I have a specific example for us to look at. And on this one, r of uv, I'm defining the first component function to be sine u cosine v, right? The second one, sine u sine v, and the last one, cosine u. And I'm asking you to restrict u between 0 and pi. That's a weird looking pi. And then v between 0 and 2 pi. And I ask here, do you recognize this? Does anyone recognize that at all? What is it? It looks like spherical. Doesn't that look kind of like spherical? Yeah. Spherical was like rho, cosine theta, sine phi, sine theta, sine phi, cosine phi, something like that. It looks, I mean, this should kind of like say, you should be like, hey, that kind of looks maybe like that might be spherical. So what I'm going to do is this. I'm going to ask you right now to just, this right here is a grid that shows, ignore this cluttered, okay? This is our u-axis and this is our v-axis, all right? So what I'm going to do is I'm going to hold one of these variables constant. So let's hold v constant first. So go up and look at this function, and what would happen if I held v to be constant? That would be a constant, right? That would be a constant, right? And then that would not be a constant. So we would basically have cosine u, sine u times a number, sine u times a number, right? And the question would be, what does that draw? Because now that's more like a curve, because it's only depending on one variable. What would that draw, right? Or I could hold the u to be constant. If I hold this to be constant, I have cosine v, sine v. Hey, doesn't that draw a circle? And then that would be a constant. So it looks like when I hold one thing constant, it's drawing circles maybe, and then the other thing constant is drawing something with sines and cosines. Let me show you. I'm actually going to do it. Let's going to make this a little smaller so you can see this together. There we go. So this is right now us holding v to be constant. If I change, there we go. If I change my u value, look what happens. I'm drawing a curve, right? I'm holding v to be constant right now, and I'm drawing that curve. Next thing I want to do is hold my u to be constant. And if I hold my u constant and change my v, I draw that. And if I put all these together, I get a bunch of that, like all that, right? And then all of it together is the sphere, right? So a parametric surface is just a bunch of curves put together to create a surface. That's all it is. It's a bunch of curves back from chapter 10, except now we have two variables to control everything, all right? All right, I'm not going to go on. I have a handout, okay? This idea of parametric surfaces is elusive, all right? It's one of these things that students have trouble with. So I have an entire handout that we're going to go through, and we're going to come up with the vector functions that draw these surfaces together as a class. And if you can do that, then the next few sections will go much better for you. If you don't know how to draw a parametric surface, the next few sections are going to be painful, all right? So let's do it. Now, I gave you the handout, but I need to add some data to that. So if I need you to add something, I'll tell you, okay? Example A. Find the vector function, r of uv, which yields the disk shown below. So let me spin this thing around so you can see it. I want you to draw this for me with a vector function. So when you look at this, the disk here is in the xz plane, right? It's in the xz plane. And so I know how to draw a circle, right? I know how to draw a circle in the xz plane, but I want the disk. And so the disk is like a bunch of circles, isn't it? It's a bunch of them. I have control over two variables, u and v. So let me start with this. Can you all see what the radius of this is from this? Yes? That should be a 4, shouldn't that? Right? My picture does not match that, right? This implies that the radius is what? 2, which means this should be 4. That's a typo in there. Is it a typo on this? Oh, I didn't put it there, did I? I didn't put it there. Okay. All right. So let me get this first one going, all right? And then we'll kind of, and I want you to raise your hand on this, all right? Because I want everyone to have an opportunity to think about this. So I'm going to define some vector function r of uv, and it has to have 3 components to it, right? All right, first thing I know, and you should agree with me on this, is that the y component must be 0. Because no matter where you are on this disk, the y value, the green, right, is going to be 0. Because you're living on the xz plane. So my middle component function must be the 0 function. Yeah? Now, that means I have to use the x and the z components to draw a bunch of circles, right? I know how to draw a circle. I use cosine theta, sine theta, right? But here I have u and v. So I'm not going to use theta. So do you agree I could do this? Cosine, you want to do u? Cosine u, sine u? Right? But the problem with this is that that would only draw me a circle of radius what? 1, right? 1 here, 1 here. So the coefficient here is 1. That would draw me a circle of radius 1 in the xz plane. I want the circle with, well, I want all the circles, right, that start with the radius of 0 and go all the way out to a radius of 2. So I need to somehow always be adjusting this number in front, right? But I have a second variable I haven't used, right? I have v. So I'm going to put v in front of this, multiply it, and that will control my radius. See, I'm using both variables to do this. Now, if I do it this way, then the u would have to be restricted between 0 and 2 pi because that will draw me just one circle, right? And then my v, which controls the radius of this disk, is going to vary between 0 and 2. Is that clear to you, everyone? Anyone have a question on that? Yes?
It doesn't matter which one you use for cosine and sine, right?
That's right.
For the x-axis.
You could have used cosine v, sine v, and then used u here, and switch these two. Perfectly fine. Yes?
So if you just had a constant out front, you just have the circle, not a disk.
That's right. If you fix a number out here, like if you put 2, 2, then all you're going to draw me is the outer edge. Yeah.
Secondary, just what if you swap the sine and the cosine?
It would still draw it.
It
Yes.
would be
It would draw it in a different, it would start in a different place, but it would still draw you the disk.
Okay.
Yeah.
I was just wondering because like looking at
The standard is cosine and sine. If you're going to go from 0 to 2 pi, the standard is cosine and sine because it draws it the way we did in pre-cal. You know, going around starting like that and going like that. Okay, you ready for the next one? Did you have a question? Yeah.
If you hold UW, if you hold U constant, would you just get a line or?
If you hold u constant, that's a good question. What would you get if you held u constant? What do y'all think? Like, think about if, let's let u be, let's do something easy. Let's let u be 0, okay? If u was 0, what would you have? If u is equal to 0, then that would become, well, cosine of 0 is 1, so that's v, right? And then 0, and then sine of 0, 0, so that's 0. And now this is a line, right? This is a linear vector function. V is going to vary between 0 and 2. So what it's going to do, it's going to draw a vector that starts at 0, 0, 0, and goes to 2, 0, 0. So that would draw you 2, 0, 0, yeah. Going down the x, it would draw you that line segment like that. And now if you change your u a little bit, maybe go to pi over 4 or something, it's going to draw you this. You have to remember the x positive is this way, so pi over 4 is actually there. Okay? Yes?
So you gotta think about it like as a wireframe.
Yeah, you could look at it like this is basically like a bunch of those. Yeah, it's a bunch of those. And then if you did the other constant being held, you would draw your circles like that, like that. So you get wireframe, which is just like on that sphere. Exactly. Just like on the sphere I showed you a minute ago, you have that wire frame, if you liked, like that. Same thing. The book starts with this example, which I think is a little complicated to start with that sphere, you know, but that's why I want to do these examples in class. All right.